Welcome back. Welcome to lecture 3 of week 6 of probability theory with actuarial applications. Today we are going to discuss the law of total variance. It is also called as Eve's law. We will see why it is called Eve's law in today's lecture. However, to set the background, what we have done so far is we have introduced a notion of conditional expectation in week 6 lecture 1. With that, we told that this is going to be a major leap because we are looking at a random variable which is expected value of y given x as a function of x gx, and when you take expectation of that gx, what you are retrieving back is the average behavior of y. That was the lecture 2 of week 6, which was law of total expectation. And then we understood that this new random variable also will have a variance, right? And how will I tame that variance, or can I derive a similar law which is similar to law of total expectation? And the answer to that is yes, and that is what is this law of total variance. So, let us understand what this law of total variance is. To understand, let us set the context. Why do we need to study this separately? In the last lecture, we found that expectation of S, which was expectation of a random sum, was a cakewalk for us. That is, it was simply expectation of the summing variable and into expectation of the summed variable. So, we were very happy with that. But what about variance of this new random variable S, right? Can we say that variance of S is variance of n into variance of x? The answer will be completely wrong. We cannot use this formula which we have used for law of total expectation in this context for computing variance of S. By the way, what is variance of S? It is a risk associated with S. So, variance of n into variance of x cannot be taken as a product, correct. So, it is completely wrong, it is not a valid rule. Okay. Then we will look at that earlier version where we were taking out a constant, right. So, when we were dealing with variance of S, we also stumbled on the fact that expectation of S is mu times expectation of n, right. So, can we use that fact which is variance of n times mu, and now as usual if I throw this mu out, it will become squared and this is nothing but variance of n. Is it correct? It is partially correct, but it is capturing the variance associated with summing variable n. It is not capturing the variance associated with the random variable for which the mean is mu, right. So, these are the two problems, that is why we cannot rely on the law of total expectation. So, what we need to do? We need to consider various variances and we need to capture them. So, in this case what we have is we have two sources of randomness. One is the random variable n, another one is the random variables xi which we have considered to be IID, right. So, now we need a tool that actually combines both these variances, okay. So, this is called law of total variance, okay. So, now when it comes to variance, we have to look at the theory of the variance, okay. To start with, let us define variance. So, what is variance? If I want to look at variance, variance of y is defined as expected value of y minus expected value of y, this whole thing squared. This is our definition of variance. Now, what does our law of total expectation say? Let us keep that at the back of our mind. If I want to talk about expected value of y, I can look at expected value of y as a tower, which is expected value of y given x to x. And remember, this expected value of y given x, we have already seen that it will be nothing but function of x. So, this is what we have to keep in mind to derive the law of total variance. So, this will be our benchmark and we will work on this benchmark. So, what I will do now is, because I want to understand the contribution from x, I will split this into expected value of y minus expected value of y given x, which I will write as g of x plus g of x minus expected value of y, this bracket, and this is whole thing is squared. Okay. So, let us understand this. Now, we will open this square up and we will try to identify individual terms. I will start from the leftmost side to have enough space on this table. So, it is basically expected value of, this is my first term. Okay. So, this is y minus g of x the whole squared, right. This is the first term that I have taken square. Then a square plus b square, which is this, if this is a and this is b, it will be a square plus b square. So, this will be g of x minus expected value of y the whole squared. Okay. Then what will happen is the cross terms, that 2ab term will come. So, it will be 2 times y minus g of x into g of x minus expected value of y. Okay. There is no square associated with this. So, this is what the entire expression looks like. So, I have from these two terms 3 terms, which I will write as, say this is the term 1 when I take the expectation, this is the term 2 when I take the expectation out, and this is the term 3. Let us handle them one by one. So, look at 3 first. This is the most interesting term, and this is actually saying you are taking expectation of 2 times y minus g of x into g of x minus expected value of y. Okay. So far I have not used this tower property. So, it is time to use this tower property, because one term is in g of x, one term is in y, right. So, I will use that tower property to evaluate this particular expectation. That is where the main problem lies. So, it is 2 times, 2 will be thrown out, expected value of y minus g of x. I am using this law of total expectation. Okay. Y minus g of x into g of x minus expected value of y given x. Okay. So, this given thing is with this, and then this is exact application of total law of total expectation. That is why this rule is called sister rule to law of total expectation. Now, look at these 2 terms. What is expected value of y? It is actually a single number. What is g of x? It is a function of x. So, given x, this is a deterministic function. That means it is a constant given x. So, what I can do is I can simply take it out of this particular expectation value. So, it is 2 times expected value of, you just remove this, g of x minus expected value of y. Why? Because I am treating this as a constant, it is a function of x and x is already being known. So, I can remove it. Now, what remains is expected value of y minus g of x given x, and then this is the expression. Okay. So, now if you look at this particular thing, what exactly is this? You can just use the definition of g of x, expected value of y given x, it does not matter So it is nothing but a constant, and this particular thing is what? So this particular thing is expected value of y given x. Therefore I can rewrite this as expected value of g of x minus expected value of y, this is separate, into expected value of y given x minus expected value of y given x. Here I am replacing gx with expected value of y given x, okay. And therefore these two terms essentially before taking expectation will mutually cancel each other. So this term will become 0. Therefore my third term is 0. Now our job is to identify the first two terms. So let us begin with first term. What is expected value of y minus gx squared? Okay. So that you can see as, what is this? This is actually a expected value of, you can open this up, y minus gx is expected value of y given x, and then I can take this squared, I can take one more expectation and take x here, again application of law of total expectation, and then you can see this to be equal to, this is nothing but variance of y given x and an expectation of that, okay. And then let us look, this is the first term, this is the gist of the first term. Now let us look at the second term, which is to be covered here. Second term is more or less similar. So I have expected value, then gx is nothing but expected value of y given x minus expected value of y the whole squared, okay. So we can, you are looking at this. So now what you can do is, you can view this particular thing, expected value of y, as expected value of y into expected value of y given x. So that's what we will do now. That means you are essentially looking at expected value of y given x minus expected value of y given x, correct, and this together squared. So which essentially means, what I am looking at is expected value of gx minus expected value of gx the whole squared, okay. So this is nothing but variance of g of x. I can write this variance of g of x as variance of expected value of y given x, okay. So now I have 1, 2 and 3. So this basically I am saying 2 is equal to this. Therefore our formula for variance of y will become now equal to, so what is 1? 1 is equal to expected value of variance of y given x. What is 2? 2 is equal to variance of expected value of y given x, okay. And therefore this term is 0 because of this result, and therefore I got my final formula for law of total variance to be equal to this, okay. So the first term is expected value of the variance of y given x, and the second term is variance of expected value of y given x. To make the understanding more clear, let me show you one visualization of this particular variance. So, here is a variance. So, our first term is expected value of variance of y given x and variance of expected value of y given x. Let us take one simple analogy of an archer. Let us say there are 3 archers which have their own variance, right. Everybody is having their own variance in hitting the targets. So, x1 is the first archer, x2 is the second archer, and x3 is the third archer. I want to compute total variance in their hitting, all of them together. So, what I did, we have split them into archer wise clusters. So, this first archer will actually hit on these spots, okay. He is hitting regularly on these spots. So, I want to capture the variance of these, okay. So, that is this capture which is denoted by green arrow. So, it is within x1 how much is the variance that is being counted here, that is essentially variance of y given x. So, we are counting that variance here. Similarly, archer x2 will have its own variance which is captured here. Because I want to quantify it, I will first take expected value of y given x2, and that is this horizontal line. Around that there is a spread, so that is the variance, okay. Similarly, for x3 I will calculate the variance. So, I have this variance, but will that give me variance of y? No, it is giving me the archer wise variance. So, what I will do? I will simply take average of these, that is what this within group noise will be captured, okay. But will this give me the complete variance? No, because all these expected values are essentially some dots in this, and they themselves have variance between the groups, right. How will I capture that? That is where this term comes. So, when I look at these expected values, I want to know, because in that cluster I want to know what is the variance among the clusters, right, all together in inter cluster variance. So, that will be captured by this term, and that is how we have a complete picture of variance. So, one is within the group noise, another one is between the group spreads, and these two terms are very crucial for understanding. So, that answers our first question, whether those variances are sufficient or not. So, the answer to that is no, they are not sufficient. I have to look at within the group cluster variance and outside the group, between the groups, okay, intra cluster, inter cluster variances, and that is where these two terms are really important for me to capture the total variance, okay. So, now about the terminology, Aves law, right. So, now you know what is variance of y, it is expected value. So, E variance of the variable, what is the variable? Y given x, expected value of the variance. So, the num EV comes, okay, and then the second term is variance of the expected value of the variable. So, that is where VE comes, Eve's law, that is why the name Eve's law. So, when you look at this particular terminology, to memorize law of total variance, it is always better to visualize it as Eve's law. So, E stands for expectation, V stands for variance. So, expected value and variance of y given x, and then next VE will come, and that VE is variance of expected value of y given x. So, you will never commit any mistake in computing the law of total variance if you remember this mnemonic Eve's law. So, that is where the power of that mnemonic comes in, okay. So, now we have understood the Eve's law. Let us reiterate the importance. when we are doing risk management of our portfolios, the formula is very important. It splits the average risk within the groups plus risk between the groups. I have shown that Archer's example, right. So, that Archer now replaced with portfolios with risk factors. Okay. So, average risk within a group, okay, that is the Archer, right. The Archer is the risk here, and within a group how much risk is there, and outside the group how much risk is there. So, all these things will be very well captured by our Eve's law. Okay. So, first thing is the first term, which is expected value of variance of y given x. When we apply in actuarial context, it is expected process variance. So, this is the variance or the risk inside the single class of risk. Archer, you replace it with 19-year-olds, that is one risk factor. And then when you take expectation of that, what you are doing is you are summing over all those risk factors, that is why it is the average. So, it covers the frequency of 19-year-old, 55-year-old, 65-year-old, all of them. You are taking the average and you have individual estimates for each groups. Second factor is variance of the conditional expectation, and it is nothing but average claim for single risk class. Okay. So, variance between those averages will measure how much 19-year-old differ from the mean and how much 55-year-olds will differ from the mean. Okay. And I will take average of them. So, that will give me average variance. So, this is the average claim for single risk class, and these are important things for us to evaluate. Okay. So, now we have done all this in order to find variance of S, that compound model, right. So, let us go to application where we will find the variance of the compound model. So, this is the reason why we used LTV. So, we want to find variance of S. How will we proceed? So, naturally this n is the dependent variable. So, I will condition on n. So, variance of S is expected value of variance of S given n plus variance of expected value of S given n. Okay. And now you will evaluate these two parts separately. First part, expected value of S given n. We already know from our lecture 2, if expected value of x is mu, this becomes n times mu, and as a random variable this is n mu. No worries about this. Second part, variance of given n, we have not calculated that, right, but given n is equal to n, this variance of S is variance of sum of IID random variables, and therefore, if the IID random variables have variance sigma square, variance of S given n is equal to n is nothing but n times sigma square. So, treat this as a random variable, replace small n with capital N, it becomes n sigma square. So, these are two important factors which are inside the inside the square brackets of this formulation. Okay. So, now we will apply this for deriving the formula. So, the formula is expected value of variance of S given n, which we know to be n mu, and expected value of S given n, variance of S given n is already known to you, expected value of S given n is n mu, variance of S given n is n sigma square. So, first term is n sigma square, expectation of that, and second term is n mu and variance of that. Okay. Okay. N sigma square, expected value of n sigma square, since sigma square is constant, it will be pulled out and it remains expected value of n. So, it is expected value of n times variance of x. Next factor, n mu. So, you take variance of that, variance of n mu will throw mu square out, and then it remains variance of n. So, variance of expected value of S given n is expected value of x square multiplied by variance of n. Put both of them together in this formula, you get expected value of n times variance of x plus variance of n times expected value of x square. Okay. Now come to our famous model of this compounding distributions, that is Poisson model. So, it is called compound Poisson model. So, you already know if n follows Poisson, this formula becomes very handy. It is very simple formula, because n, if it is Poisson lambda, we already know this is the only distribution with mean equal to variance. So, your mean and variances are same. So, how will this translate in simplicity? Let us look at variance of S is expected value of n into variance of x plus variance of n into expected value of x square. Both of them are lambda. So, lambda is taken out as common. So, variance of x plus expected value of x square, this is nothing but expected value of x squared. So, it becomes lambda times expected value of x squared. Okay. So, the formula becomes very handy. Yeah. So, it is lambda times expected value of x square. So, it is very easy to compute. You just need to know the underlying random variable x and compute the second moment of that. So, let us look at this problem where we will solve this problem. I have n following Poisson lambda, severity claim has expected value 500 and variance of x equal to 75,000. You are asked to find expected value of S and variance of S. How will you proceed? Expected value of S is very straightforward. It is expected value of n into expected value of x. So, 100 into 500, you have 50,000. Nothing great about it. How to compute variance of S? For that we have law of total variance. So, let us split it into two parts and get the answer. First, variance of S is expected value of n into variance of x plus variance of n into expected value of x square. We already know expected value of n is 100, variance of n is again 100, variance of x we are given as 75,000 and expected value of x square is 500 squared. So, that is also known to me. So, I will simply put everything, and what I got is 7.5 million plus 25 million, which gives me 32.5 million. Okay. So, that is the answer, 32.5 million. Let us look at the other way, which was lambda times expected value of x squared, right. So, what will it give me? You just simply have to find the expected value of x square. So, 75,000 into 25,000, which will give me 3,25,000 multiplied by 100, it gives me 32.5 million, right. So, in both ways you can easily compute the using the law of total variance, variance of S. Okay. So, we have seen actually how to handle the compound Poisson model, which is very difficult to handle and it is a lifeline of actuaries. So, let us summarize what we have done in today's class. We have seen how to decompose variance into within and between components. In the course, we developed a powerful tool, which is law of total variance, expected value of variance of y given x plus variance of expected value of y given x. First term is within the class variance, second term is between the class means. Okay. So, now the shortcut that we derived for compound sums is, in general, if I have to compute variance of S, it will be expected value of n into variance of x and variance of n into expected value of x squared. For Poisson case, it simplifies to lambda times expected value of x square. Okay. So, what comes next? We have covered lot of ground. So, we have used law of total expectation, law of total variance. Now, we will actually use these two laws to get something more, which is mixed distribution, where we assume the parameter of the distribution also had some uncertainty, and how to handle those cases. These cases are one of the important questions in exam. Okay. So, we will see that in the next class. See you in the next class. Thank you for listening to this class.